Physics, radiation and half-life. So for this example, we have a radioactive molecule that is decaying. It's 13153I, and it has a half-life of approximately 8.07 days. So if we initially have 10 kilograms of this substance, how much will we have in 3 weeks from now? So for this problem, we can go ahead and outline our knowns. We have a half-life of 8.07 days, a period of 3 weeks, which is 21 days, so that we can have consistent units. And then our initial amount of material is 10 kilograms. And what we're looking for is the remaining amount of material that we have, and that will be measured in kilograms as well. So the basic formula for half-life, or calculating how much you have left, is your remaining material equals your original amount of material times 1/2 to T. And this T is basically the period of time over the half-life. So in this case, the period of time is going to be 21 days, and the half-life is going to be 8.07 days. And thusly, T is going to be equal to 2.6. Alright. So with that, we can go ahead and plug this into the equation. And so for our remaining, or which we'll just call M final, or our final mass, is equal to our M initial, or our original mass, which is 10 kilograms, times 1/2 to the T, which is 2.6. Now when you solve this out, you come up with M final, or the remaining amount, equals 1.649 kilograms of 13153I. Alright, and then also for this problem, we wanted to cover a little bit more about radioactive decay. So there are 3 different types of radioactive decay, and these are alpha decay, which is basically just a high energy proton. It's not very strong decay. It can be stopped by a piece of paper, and it's not terribly damaging, basically to like your skin or so forth. Like an alpha particle would be stopped by your skin, so it's not very strong radiation. For beta decay is given by a B. It is basically a high energy electron, just a free electron, and one of these electrons could probably be stopped by a sheet of metal, probably not like aluminum foil, but something a little bit thicker than that, and that would stop or deflect an higher energy electron. So with gamma radiation is by far the most dangerous for humans, but we don't see it very often. It comes out a little bit in medical technology and in physics experiments, but for the most part this is radiation that is generated through nuclear reactions. So like the sun is a great big nuclear reaction happening, and it produces large amounts of gamma rays that are filtered out by the sun's atmosphere and then the Earth's atmosphere. So we don't really see them very often. But basically these are high energy rays that are produced basically as balances to linear and angular momentum that happen in nuclear reactions. They're very hard to stop, very high energy. It takes at least 5 inches of high-density material such as lead. Newer materials, they've managed to cut down some of the distances, but for like the construction of nuclear power plants, they still use several feet of lead and concrete to prevent any radiation from escaping.